my pleasure today to welcome Dr. Jacques Dufour, if I pronounce that right, from Paris, France. I first met him 2 years ago at the co-fusion meeting in Hawaii, and he's also in this meeting in Monaco last month. He got his degree as a chemical engineer from the, if I translate to French, is to be the National School of Mines in Paris in 1961. And he's been working for Shell Company since 1964. And part of that time he was since the end of 1994, Dr. Dufour has been working full-time on cold fusion at the, and if we translate that, it would be the National Conservative of Knowledge and Industry, arts and meters. But he told me before the seminar that would be equivalent to knowledge and industry. And his title today is Excess Energy in the System, Palladium Hydrogen Isotopes, Measurement of Excess Energy per Atom of Hydrogen. So I'm happy to turn the time over to Dr. Dufour.
Thank you. First, let me say that I'm very happy to discuss this problem with you. You are probably aware that excess energy production has been widely reported when studying the system Palladium, deuterium. Other systems are also be reported to yield excess energy like nickel, normal hydrogen. I think the key issue in this field is to first check that it is a true excess energy production, which is already very difficult. When you have done that, the next step, which is even more difficult, is to try to explain that excess energy production. The very first explanation which was given was so-called cold fusion, a type of nuclear reaction between the hydrogen isotopes occurring at room temperature, which then should yield helium-4, helium-3, gammas, etc., a list of products which are well known. So the second step in the study would be to correlate the excess energy production with a number of so-called nuclear ashes, and the overall balance should be correct to be sure that this is the right explanation. So my talk would be in fact, the study I carried out in France was in two periods. The first period was between 89 and 93, and I carried out the study, like many of us working in cold fusion, on not on my normal work, but on extra hours. So the first period was to check that there was in fact an excess energy production, and I will show you just a summary of the results, which are not very, I would say, spectacular, but from a statistical point of view I think they are representative. So after this period, the company, the Shell company, who was interested in the field, of course, because it's energy, gave me the possibility of checking whether there were nuclear ashes or not in the system in a laboratory which had the expertise to do that, because in Shell we of course we had a very small team dealing with radiation measurement, but we are not experts. So my sponsors thought that it would be better to send me in a laboratory expert in measuring radiations to correlate the excess energy I observed with what we could measure. And that's the second period of this study, which was carried out in Paris, in Conservatoire National des Arts et Métiers, which, like many organisms in France, was founded just after the revolution. And there is a laboratory there, which is a Laboratoire des Sciences Nucléaires, which is in fact expert in measuring radiations. Okay, so I will, just to start, I will show you, or let me say first that I use a system which is different from the one which is usually used, which is electrolyzing heavy or light water. I'm operating in the gas phase. That is, I'm in fact making discharge either in hydrogen or deuterium, with various systems, but at atmospheric pressure, and using one of the electrodes being made of palladium or nickel alloy. So it's slightly different from the electrolysis of water. You can say that it is a gas phase electrolysis. It's completely different, but it doesn't matter. So just to start with, I will show you a summary of the excess energy production which I observed in the first period of the study, that is in the Shell laboratory in Rouen. Rouen is a town very close to Paris.
Maybe it's lights.
Yeah, maybe because it's faint. So this is the summary of 100 experiments. Each experiment was lasting between 1 week and 3 weeks, because it's very hard to make a representative experiment on very short periods, because you are always on an unsteady state situation and you can see anything. So these are the summary of 100 experiments, and you can clearly see two families of points, one family here and one here. These two belonging to this family. These are reference experiments. They are experiments which should not yield any excess energy. Here you have the number of experiments. This is the experiment sequence. And this is the excess energy. In fact, it's the excess power. Excess power expressed in watts. The reference experiment include heating the system by resistors, heating the system by discharge in nitrogen or argon, or heating the system in a way on which I will give more details later. That is by making a discharge in hydrogen or deuterium with no gas, with no metal in contact with the discharge. So I will explain that later. So all these experiments have yielded zero excess power with a standard deviation which has been calculated, which is 0.45 watt. So the reference experiments in this series have yielded 0 plus or minus 0.45 watt. The total input power was 30 watts in that case. These experiments were run with the discharge made either in hydrogen or deuterium with a metal in contact with the gas, the metal being either palladium or stainless steel, which was taken because in stainless steel you have iron and nickel, which are two metals that you can make metallic hydride like palladium, but with a different loading ratio, of course. So you can see that all these experiments are above the background, and the average is 1.85 watts with a standard deviation which is similar to this one, which is 0.42, something like that. So there was clearly, on a period of, this is 8 months, something like that, 8 or 9 months, with various dismantling of the system. I mean, it includes, the standard deviation includes undoing the equipment, redoing it and rerunning it, etc. So it gives the robustness of the system. And you can see that there is statistically a significant excess energy production in this system. So this work was done between 89 and 93, and what I am going now to give you in more details is the result of the second period of the study, which is for the time being carried out in Paris in Conservatoire National des Arts et Métiers. And I will give you the results for the search for the nuclear ashes and radiation in both systems, hydrogen palladium and deuterium palladium. Then I will give you some new results on the excess energy on the system using only pure palladium and pure hydrogen. And then I intend to finish on an hypothesis, which is still a real hypothetical hypothesis, to explain the results. To be completely clear, the search for nuclear hashes has been made on the reactor which were used in the first period, okay, the period 89-93, and these are results which are obtained with a completely different calorimetric system which was built in Conservatoire des Arts et Métiers to check, in fact, the first excess energy production observed in the first period. Okay. So I will give you first indication on this and then elaborate more in details on this system. So I just told you a few minutes ago that the search for nuclear ashes and radiation was done with the reactors used in the first period study. This has been described for those who might be interested in the publication of Hawaii ICCF 4. Typical power around 2 watts. These, I think, are important figures to keep in mind. For 1 watt, if you are explaining the phenomenon with classical fusion reaction of light hydrogen or deuterium, sorry, then you should get helium-4 and gammas in the order of 10 to the power 7 per second for 1 watt, helium-3 protons, tritons and neutrons 10 to the power 12 per second. This gives you the order of magnitude of the product we are looking for. There are a number of explanations, which are for the time being only hypotheses, that all the reaction would yield helium-4, which would be different from the hot fusion reaction, of course. If this were the case, you would expect 3 10 to the power 11 helium-4 per second for 1 watt. So these are the order of magnitudes we are looking for. What we have monitored were in fact all the products except protons, that is helium-4, helium-3 and tritium. And as regards radiations, we have looked for neutrons and for X or gamma photons. So I'm going to come to the conclusion. I have more elaborated data, of course, but it would take too long to discuss them. Helium-4 and helium-3 in trace amount are very difficult to measure because you always can have pollution for the atmosphere, and it's very well known. Just as an anecdote, it was a debate between a chemist, which you might know, which was called Panet. In 1934, this chemist Panet published in Nature at the time an article saying that he could transform deuterium into helium-4 just by, in fact, contacting deuterium with palladium. So it was more or less the beginning of the so-called cold fusion. And he was, I would say, completely Rutherford demonstrated that, in fact, helium-4 was leaking from the atmosphere through the pyrex of Panet's reactors, in fact. So the debate on the origin of helium-4 on all these experiments is a very old one. So helium-4 and 3 are difficult to measure. What we have used was, of course, a high-resolution mass spectrometry with various getters in it to increase the resolution by getting out the hydrogen, deuterium, and all the nitrogen or oxygen, etc. So then you have a very nice resolution on the peak on helium-4 and helium-3. For the gas phase, we have sampled the samples in a stainless steel reservoir, but of course the reactors are made of Pyrex, so that's a problem. The electrode was melted by fusion inside the mass spectrometer, and they had a very small furnace heated by iron beam inside the mass spectrometer, so there is no air pollution on the results on the electrodes. Tritium was determined by conversion to water and then by scintigraphy. We worked, in fact, we were working with expert laboratories in the various fields. So this measure has been done by people who are very well trained and very expert in measuring helium-3 and helium-4. And the result, after much discussion with all these expert people, was that helium-4 and 3 in the gas phase, which we found more than, by making balance, of course, we found an apparent production, but it was coming very likely from air. We found, because we measured neon, of course, with helium to trace in a leakage from the air. Neon-22 was measured. The ratio of helium-4 on neon-22 in air is 3.3. The average from the experiments with hydrogen was 5, and for deuterium was 6. And 6 compared to 5, so it means that there is an entrance of the helium from the atmosphere somewhere, with an increase of the helium concentration compared to the neon. And the difference 6 to 5 is not significant. So the conclusion is that what was found in the gas phase was coming from the air. We found some small amounts of helium-4 and helium-3 in the electrodes. Of course, there is an obvious artifact in that, which is ion implantation. As far as you have helium in the gas, you can implant these helium-4 and 3 in the electrode just by discharging on it. It's a very well-known process. We think that most of the helium found in the electrode is coming from by this mechanism, finally from atmospheric helium. But we must notice that the ratio helium on neon is 30 compared to 6, 13 in the electrode compared to 6, so there is more helium compared to the neon in the electrode than in the gas, which can be explained by the mechanism of ionic implantation. But this would take 2 years study to discriminate whether or not it is ionic implantation. We found a much higher figure in one experiment. We found 120, but again this was on hydrogen, not on deuterium. So you see that the results are not conclusive on deuterium making helium-4 because of these figures and this figure. Anyhow, I think in that case you play the doubt and you say, let's suppose that these things are really a production from a nuclear reaction. Then you can give upper limits and say, if I have a production of helium-4, helium-3 and tritium, these are the upper values. And these are the upper values we find. For helium-4 is 10 to the power 5 per second. Here is 5 to 10 to the power 3 per second, and here 10 to the power 3 per second. We had, with a good statistical background, 1.8 to 2 watts excess energy production. So you can see that there is a 10 to the power 6 or 7 discrepancy between this and the observed excess energy. So that's the first problem you are faced with, I was faced with my friend in Paris, that we had a good statistical results on excess energy, but we had, or even if we were making something, it was not the explanation, okay? And you will see that it's the same thing for radiation. What you observe for radiation is what we measured, in fact, is neutron. We took an helium-3 counter because BF3 is not reliable. 2 helium-3 counters were used with different windows. I'm not going into details. X and gamma photons by an ionization chamber, and also by scintillation, solid-state scintillation counters, sodium or cesium iodide, with the, of course, energy spectrum. What we found, mainly, basically, I will show you some records. Neutrons, typically background, whether it was with hydrogen or deuterium. Photons by ionization chamber is background. We observe from time to time, and it's getting maybe more reproducible now, but I call them, for the time being, low energy signals on these apparatus. I'm only taking the term of signal because when you are using the type of discharge I'm using, you can have some electrical pickups on these things, which have been reduced to a very low level, but anyhow, for the time being, all these are only signals. Just to give you an idea of the neutron measurements, this is the record on, I think, 6 or 7 months. We recorded the number of counts on 2 helium-3 counters. This one has a wider opening than this one. That's the only difference. And we have plotted, well, you can see that you have fluctuation. It's in counts per second divided by 1,000. So it's 0.003 Newton per second, count per second. You can see that you fluctuate from 30 to 55, so that's nearly 2-time fluctuation. But when you correlate that with the experiments, this is an experiment where we increased the power, then we stopped it, then this is another experiment when we increase the power. So if you just concentrate here, you say there is a correlation, but if you look at the whole range of 6 months, you see that there is no correlation, in fact. Because you have period where the increase of power gives increase in the counts, period where you have nothing and you have also an increase, or here. Here we had no experiment, and you can see the level here was nearly this one. And there was no experiment. Here, it's a beautiful result, but there was a neutron source. Of course, that was to check the counter. So the main conclusion from the neutron measurement is that we were only looking to background fluctuation, and that the background fluctuates in a ratio of 1 to 2 or 2.5. I think I discussed that with experts, is normal. So if there is any neutron production, it is somewhere in the background, so it's very low. And same for the ionization chamber. So the conclusion then was the excess energy measured in the first period true? Because when you cannot find any correlation between what you have measured and what you expect, then you must ask you the question, were my first experiments correct? So we have rebuilt a completely different calorimetric system with more measures, etc., which I will describe somewhat slightly lengthy because I think it's important to insist on the experimental conditions. And we really arrive at the conclusion that from the excess energy production, something very strange is happening, and that the expected ashes from the classical nuclear reaction are not there. So I'm going just to give you some indication of the materials we have used for this experiment, a brief description of the reactors, of the calorimeter and the calibration procedure, and the hydrogen measurement, hydrogen loading ratio, and the results we have obtained. The experiment, well, I have run some experiment with deuterium, but we have, for the time being, we intend to go back to deuterium later. We have first concentrated on the system hydrogen-palladium, because hydrogen is simpler than deuterium, and we have tried to use palladium as pure as possible. So the hydrogen is alpha gas N55 with these impurities in it. The palladium is a Johnson-Matthey. They sell it with this quality guarantee. I'm not sure that this is true. For the time being, I have analysis being carried out in samples, and I think we will find figures higher than that. So the puratonic Johnson-Matthey is not that pure. And we have used two shapes of electrodes, either foils 0.1 millimeter thick or wires 0.25 millimeter diameter. In the first experiment which we ran in the first period in Rouen in Shell laboratories, I used what is known in the people who are knowledgeable in gas discharge as faint sparks. That is, sparks of a low energy sparks, which you can control by the electrical setup. And also we have used in Rouen ozonizer type discharge. Probably not very well in detail of what is that, so I will give you some indication. In the new system we have built in Paris, we have used only ozonizer type reactors with a Pyrex dielectric wire, and we have used two types of ozonizer reactor, one with one dielectrical wire and one with two. I will give some comments on that, because when you are using this type of reactor, you can run experiments with a discharge in hydrogen with absolutely no metal in contact with the discharge. And that's very interesting because it can be a very representative Planck experiment, because you are creating exactly the same discharge in the gas, but there is no metal in contact with the gas. So I will give you a very brief indication on why that can. This is the electrical setup of a ozonizer type discharge. Let me start by this one, which is slightly easier. Both reactors have a cylindrical symmetry. So what is represented here are tubes, in fact, with an axis here. Okay? And of course, this is cat because we have entry of gas, outlet of gas, which I don't represent here because it would be too complicated. The electrical alimentation is from the circuit is very simple. I have here a high frequency, low voltage generator, which with voltage can be raised to 220 volts, and frequency varying from 50 to 5,000, because to carry out this type of discharge you need an AC current. You cannot do it by DC current. And there is a coil here. There is of course a power measurement here, and a high voltage, high frequency which is delivered here. So let's start by the easiest reactor to be understood. So it's the same of course alimentation here. You have here the axis. So a ozonizer discharge, you have two electrodes. One electrode is here, okay? And one electrode is here, and that's a palladium wire, 0.25 millimeter diameter. But between the two electrodes, you have a dielectrical barrier, which is Pyrex, which means that you cannot arc between the two electrodes, which would happen if you had no dielectric barrier, because only the field is shielded by charge deposition here. I don't want to go into detail, but at atmospheric pressure, you get a kind of glow here around the wire, which is different from a low pressure discharge. It's a way of spreading evenly a discharge on a wire, and this is extensively used to generate ozone, by the way. So this is one dielectric barrier, and here you can see that palladium is in contact with the discharge. Okay? If you look at the two dielectric barriers, it's slightly more complicated, because you have one of the electrodes is here, the second electrode is here, but you have two Pyrex tubes here, which prevent contact between the two electrodes and the gas. The discharge happens here, and this is a palladium foil, which is at a floating potential between the two electrodes. And what you can do, what I did of course, you can do experiment with this foil in place, or you can withdraw this foil, and if you withdraw this foil, you have a discharge here with no palladium in contact, with no metal at all in contact. And this is a good plan. Okay, so I will give you then the results, not the result yet, but show you. Well, this is just to show you how it looks really like. This is a one wire reactor, and you have two wires here, a copper counter electrode and a Pyrex here, which is in fact part of the system with the feeding gas, etc., etc. Okay, and that's only a what do you call that? Circulation of the hydrogen just by thermal effect. So this is for the reactor. Then a brief discussion of the calorimetric system. One criticism I had for the first system I used in the first period was that I was using three calorimeters. One for the signal generator system, which generate alternating signals to be feeding the coil. A second calorimeter with the high voltage coil, and a third calorimeter with the reactor. In this new series of experiments, I'm using only one single reactor. The major part of the heat is recovered in a flow of silicon oil, which is flowing, as I will show you how, through the calorimeter and through the reactor. Here you recover 95 to 99% of the heat. The rest is exchanged with the air of the lab, which is regulated, of course, but you have an exchange of heat. And this is determined by calibration, giving a relation between the heat lost through the air and the difference of temperature between the calorimeter and the air. This is a classical way of calibrating the calorimeter. At least 20, we record the flow of oil, the power inlet, which is measured by a numerical wattmeter with high sampling frequency, because you need to have a very accurate measurement of the electrical powering. I won't go into detail, but those who are interested will ask questions. I record 12 temperature in various positions of the calorimeter, etc. And all of course, record the flow of oil, which is checked by gauge flask measurement with the calorimeter, with the chronometer and gauge flash. You can check that the oil flow is correct. All these data are sampled every 15 minutes by a data logging system which allows complete balance, thermal balance to be made. So this is basically how it looks. There are two flows here. There is one flow of water surrounding the calorimeter here, which is maintained at a 20 degree plus or minus 0.1 by a cryothermostat here. And there is a flow of oil here, which is flowing like that, which then goes into the calorimeter in a coil which is around the reactor to recover a maximum of heat, which would be flowing like that. And then the oil is passing through the reactor here and is out here. The temperature is measured here, here. The flow is measured here, corrected of course for temperature, etc. The only leakage of air of heat is mainly through here and here when there is no circulation of water. Now we'll give you some indication of how the calibrations of the system were made. In fact, we have run calibrations with various ways of heating the system. We have used, of course, resistors, and we have used resistors with various cosinus phase, varying from 1 to 0.35, because this might have an influence on the precision of the wattmeter. Because the wattmeter which was used is a numerical wattmeter which samples the current and the intensity, makes the products, and then gives you the correct power. So it's not, it's a real measurement, but the cosinus field, the dephasage can have influence. We saw no influence, in fact. This was done because the discharge introduced a very low cosinus field in the system. We have run discharge in argon with palladium, the reactor equipped like for hydrogen experiment, but with argon. And we have run experiment in hydrogen with the double dielectric wire, that is with no metal in contact with the discharge. What is remarkable is that all calibration, of course, are on the same correlation. I will show you that. The typical standard deviations are 0.3 watts for one experiment lasting 1 month. If you run several experiments, one after the other, then you have to dismantle the calorimeter to re-put it in line, etc. Then if you take the standard deviation for 4 experiments, including 3 complete dismantling, then you find a standard deviation of 0.7 watt. That gives you a good idea of the reproducibility of the system. And this is for an input power up to 130 watts, something like that. I will show you the calibration curve. Here you have the difference of temperature between the oil, the calorimeter in fact, and the lab. And here you have the losses expressed in watts. That is in fact the difference. This figure here is the difference between the heat recovered in the oil by multiplying the flow of oil by the temperature difference in and out, taking into account variation of temperature of the variation of specific heat temperature, etc., etc. And so you see that the relation with the difference of temperature is good, that you have a linear relation between the heat loss, that is what is leaking from the system, which represents, I told you, some between 1 and 4%, because at the level of 100 watts, this is 1%, this is 4%. And the standard, this includes Well, these, for instance, figures are hydrogen in a double dielectric barrier. So this is exactly the same discharge as the one which I will be running later. This, I think, is argon, and these are resistors. This, I think, is with cosinus phi 1, and this is with cosinus phi 0.3. So all the figures are on the same line. I will give some indication on the second graph later. But let me first give you indications on how the hydrogen consumption is measured. Of course, the system here is different from electrolysis. You don't have gases to recombine, etc. You just measure what the system is absorbing as hydrogen. And the measure is rather simple, because the hydrogen feeding system is the following. There is a small reservoir here, 300 cubic centimeter, which is filled with hydrogen or deuterium. In that case, it was hydrogen at the beginning of the experiment. The initial loading is 5 bars, and the pressure at the end of the experiment can go down to 1.5. Here, there is a pressure regulating valve, which maintains a constant pressure in the reactor. Of course, there are small fluctuation of the reactor pressure due to fluctuation of temperature, of course. There are small fluctuation here due to the lab temperature, but these are the temperature. All these temperatures are measured, so the correction can be made. The pressure here is recorded, measured and recorded. It is recorded with a gauge, and it is measured with a high precision mechanical watt pressure gauge. Same here, the pressure is recorded and also measured manually. So with all these data, you can make a pressure balance of the system, and you can see the consumption of hydrogen with time. As we are dealing with the system hydrogen palladium, we can express, of course, the consumption in millimole of hydrogen, or you can take a different unit, which is the loading ratio. What is the loading ratio? For people who work in the field, it's a very important parameter. It's the ratio, the number of atoms of hydrogen loaded per atom of palladium. Okay? So knowing the amount of palladium you have in the reactor, you can express the hydrogen consumption either as a loading ratio or as millimole of hydrogen, just by dividing the millimole of hydrogen consumed by the millimole of hydrogen of palladium in the reactor. So these are two different ways of expressing the results. So this is for the measurement. Now, we have run 5 experiments on hydrogen, lasting something like between 3 weeks and 1.5 months. And for the time being, we have run 1 experiment with deuterium. So I will concentrate on hydrogen. What we have observed first is that there is no excess energy when the loading ratio is less than 0.5, like 0.7 atom hydrogen per atom palladium. We have measured excess energy up to 5 watts when the loading ratio is higher than 0.7. And we have a very strange behavior. I still don't understand what's happening, because I've been thinking and making experiments on that for like 8 months. There is a very strange behavior of the apparent loading ratio. That is, we have an unexplainable consumption of hydrogen in the system, which cannot be easily explained. I will go more in detail in that way later. This has been observed with foils. The experiments with foils of palladium, not all the experiments were a success, and the experiment which didn't work, when undoing the reactor, we find the foil covered with scales, and without entering into detail, we can understand why with this evolution of the palladium in the reactor, a high loading ratio cannot be achieved because there is leakage through the scale. Well, it's a bit complicated, but and then the loading ratio cannot be increased, and there is a good correlation. There is no heat release in that case. I'm going to show you two experiments. One with a palladium giving no excess energy, that is at the end was partly exploded. Exploded is a big term, not from the surface of the metal. And one experiment, which of course I'm taking the best one, but I have others, giving 5 watts excess energy and a very strange behavior of the hydrogen consumption. So, what you have here on these two graphs is, on the bottom one, is the excess energy expressed in power, excess power production as a function of time for this experiment. You can see that this experiment has lasted 1.5 million seconds, which I think is 3 weeks or something like that. We increased the power from stepwise to nearly 100 watts. We always start an experiment with a calibration here, and after the stop of experiment there is also a calibration. Okay? So what you can see that this experiment in fact has yielded no excess power. We can even say that this small increase here is within the background, within the noise of the measurement. So basically this has yielded no excess energy. And you can see that the background is very well maintained in the system with this calibration. If you look at the hydrogen consumption, the hydrogen consumption in that case is expressed as hydrogen on palladium ratio. In this zone, you can see that this ratio is increasing. That is, you are putting hydrogen in the reactor, and the hydrogen is going into the palladium. Okay? So you can see a normal behavior at the beginning, when you start making a discharge in contact with palladium. In fact, what you do is that you are building a great amount of atomic hydrogen, and on top, of course, of hydrogen ions, you are making a lot of atomic hydrogen, and you have a pressure of atomic hydrogen around the metal, which is, of course, higher than what you have under normal conditions. If you put a piece of palladium in hydrogen, you have only molecular hydrogen in contact with the palladium. If you strike a discharge, then you get much atomic hydrogen, and the equilibrium is shifted to higher value. In this experiment, in which the palladium didn't behave correctly, while we achieved the normal, usual loading ratio, which is 0.7, 7.2, 7.2, 7.3. These are typical values which can be obtained for the equilibrium between hydrogen and palladium. And then this loading ratio remains stable for the whole experiment, which basically means that you have no hydrogen consumption, because you are not increasing the hydrogen in the palladium, so no hydrogen is also coming from the reservoir for all this period. So this is a completely normal behavior, no hydrogen consumption except the first loading here, and no excess energy. And I will show you a very strange result on the palladium which we're working. Palladium wires apparently work better than foils, and these are the results. Let's first look to the excess energy. It starts very low, in fact, but you have a trend of increase here. Here you start to be significantly different from the baseline. What we did here the power here was around 100 watt and here around 120 and 30 watt, the input power, total input power. What we did here was to increase the flow of oil circulating through the calorimeter, meaning that we decreased the temperature, because for the same quantity of heat, if you increase the flow of oil running through the system, you will decrease the delta T, of course. And what we observed is very quick increase of the hydrogen consumption, very, very fast. We had a drop in the pressure of the reservoir. Of course, all this is corrected for temperature variation, of course, and it's not only the variation of temperature. So there was a very fast increase of the hydrogen consumption, which was followed by a very fast increase of the excess energy production. In fact, we did that to check our calibration coefficient, because we thought that if it was slightly wrong, by increasing the flow, we would see a decrease, in fact. So what we see was exactly the contrary, and it seems to be related to the temperature of the reactor, which can be explained. And the run, well, we decided to stop the run here. Maybe if we had continued, if there was a trend of increase of the power. So this is the first thing, and before going to the hydrogen consumption, I will go back to the calibration curve. And you can see that, well, this is a calibration curve. This is the beginning of the experiment, which of course is in the same area of points. Then you start to go out of the correlation, and these are points which are 5-6 miles above the calibration curve on a period of 2 weeks. Okay, so these points are really excess energy and production. Correlated then with that is something extremely strange, which is reported on the figure, on the graph above. Again, here is the time, and here is the hydrogen on palladium ratio. I won't say much on this one, which is the ratio on the resistivities of the Y of palladium. So what we observe is extremely strange. We have a normal behavior here. At the beginning of the experiment, we load the palladium to 0.7 or 7.5, 75. Then, this is 1 day, 2 days even. So it remains more or less stable here. And then, it starts increasing. With periods of 1 day which are stable. Well, this can be in fact the noise of the pressure measurement and this fluctuation. But the trend is an increase. And to reach what I call apparent loading ratio of 5, this means that you are consuming hydrogen, of course. If you assume that all the hydrogen is in the palladium, then you arrive at a loading ratio of 5, which is completely impossible. This is completely impossible because the highest loading ratio observed in a system hydrogen palladium using hyperbar pressures, experiments have been run to 3,000 or 30,000 or 100,000 bars of hydrogen, then you reach 1. You reach a loading ratio of 1, and this is explainable by the size of the hydrogen compared to the size of the actual octahedral sites available in the palladium. So this is the maximum. So there is something extremely strange. And again, when stopping the experiment, you remain stable here, and you go back to the background here. So it's a very strange behavior, because it means that either the loading ratio of the system of the palladium is 5, or hydrogen is leaking through the system, which apparently is not the case, because when you stop the experiment, the pressure of you have no consumption, you have period with no consumption, so it's extremely strange. It can of course mean that you have combination of hydrogen with other material in the reactor, but we have checked all that, and I will give you the check. But first, I would like to present another graph, which I think is also very surprising. With all the data available, you can plot, well, this is power, with a point every 15 minutes, so you can very easily have the cumulative energy as a function of time. Just multiply the power at each point by 15 minutes, and then you get, and sum it, and then you can get the cumulative excess energy production expressed in joule, and you can plot that against the cumulative hydrogen consumption. You can do the same for the hydrogen consumption. You can accumulate the hydrogen consumption from the beginning of the experiments. And again, this is very strange. So this is the cumulative hydrogen introduced in the reactor, and this is the cumulative excess energy in joule. I put this one in order to show you that when I'm drawing two lines here, it's correct. Because you can see that this is a first period with steady state situation, and you can draw a line here. This is a second period with steady state situation, and you can draw a straight line here. This is an intermediate period which is a bit too short to draw a straight line, but it seems that there is a line here in between the slope of this one and this one, but which is extremely surprising. The meaning of this slope, of course, this slope is the excess energy per atom hydrogen. Okay? And here you have a figure of 6,000 eV, and here 1,500 eV. So this is, of course, enormous, because the combustion energy of hydrogen is 1 eV. If you take one atom of hydrogen and combine it with hydrogen, you get 1 eV. So it's much higher than the chemical range, but of course it is lower than the nuclear range. Why is it that we have various slopes? It seems to be related to the conditions in the reactor, the temperature and pressure conditions in the reactor. This is not an explanation, it's just to give you some figures. The total power in was 115 in the first period, 150 in the second and the third. The reactor temperature was 56 here and 69 here, and despite the same power here, by increasing the oil flow, the temperature of the reactor decreased, of course, from 69 to 50. You can see the figure is here 1,500, here is 6,000, and here in between 4,000. So it seems that when in a steady state situation of the reactor, that is in a given set of physical parameter, the excess energy per atom hydrogen is constant. So that's the first conclusion. So it's very strange, because it's not in the chemical range, or at least in the usual chemical range. So we tried to find some explanation of the phenomenon, and we have made a number of investigations. This is the overall balance of the system. There were 5 millimole of palladium. We have consumed 26 millimole of hydrogen. There are 195 millimole of copper at the end of the reactor to connect to the hydrogen filling system. There is 33 millimole of steels, and there is a mass of 75 grams of pyrex in contact with the discharge. And this is 1,200 millimole of pyrex. Well, this is the balance. The runtime, 40 days. The overall balance, the mean value of hydrogen consumption per atom, the excess energy production per atom is 3,000 with this 3 value. If you want to explain It's known, I've discussed that with experts in the field, that when you deposit electrical charges on a dielectric, which is the case of an ozone-energized discharge, you can modify the product itself, the substance, and you can change its parameters, specificate or whatever. So, or you can have a phase transition with excess energy production. If you would try to explain the excess energy by the action on the pyrex, you would find figures of 70,000 joules per gram, which is again completely out of the normal physical-chemical range. We looked also for a possible nuclear explanation, of course, because when you take two hydrogen, you can get this reaction. This is well known to be the PEP reaction in the sun. This is a positive electron, a positron, and of course a positron in a metal is very quickly annealed and gives two gammas of 500 keV. We didn't see any of these gammas, so it's not this reaction. So we have traced all possibilities, and we, for the time being, we don't see any.
To that number you had.
Sorry?
You had a number 68 kilojoules per gram of pyrex as one expression of the energy.
68, yeah. This one.
Okay, that's 68 kilojoules per gram, and if you just take a formula unit as SiO2, that would be about 1 joule per mole of that formula unit.
Yeah.
And what you're saying is that there's no way to explain in some chemical reaction getting 1 joule per mole. Is that what you're saying?
What I was saying, I'm taking the pyrex as more complex than SiO2. You have, of course, you have the sodium, etc. with it. And what I'm saying is that the phase transition, which could be, I would say, put forward to explain the excess energy, give much lower figures than this one, 1% or something like that.
I guess what I'm saying is that number is about 1 kilojoule per mole, which in my way of thinking is a pretty small amount. Let's say one-tenth of the energy of a hydrogen bond.
Yeah. You have 75 grams, and you have 5 million joules. So if you divide this by this, you obtain this figure. Now, what you say is that you can explain that by chemical.
Well, I don't have an explanation, but that's a pretty small number.
It is smaller, of course, than all these. I mean, what you say is, if you let me give two comments. Of course, if you look at the combustion, the combustion of hydrogen present, you will get this. So the combustion of hydrogen is clearly out of the range. Okay? You cannot explain the excess energy by that. In the case of the pyrex, you have at a lower level. But what is expected if pyrex would have given excess energy, you would have seen it on the reference experiments with hydrogen with no metal in contact. We have run